CH5.3 Diagonalization of matrices. First, we define diagonalizable matrices. An m by n matrix A is diagonalizable if A can be written in this form. A is PDP inverse for some invertible matrix P and diagonal matrix D. In other words, A is similar to a diagonal matrix D. So what's so great about diagonalizable matrices? And why is it in Chapter 5? In Chapter 5, we are talking about eigenvalues and eigenvectors, right? What's the connection between diagonalizable matrices and eigenvalue and eigenvector that we have talked about so far? Let's get to that now. Suppose we have A that is diagonalizable. So by definition, A is equal to PDP inverse. We can write it in this form. And that's multiply P on both sides. We get AP equal to PD. Suppose P is this matrix. It has n columns. So we write down the n columns of P. P1 to Pn. AP equal to PD. Now let's write P in this form, P1 to Pn, and also PD. So we have P1 to Pn, and D is a diagonal matrix, so we put diagonal elements D1 to Dn. So on the left hand side we have the product AP, and on the right hand side we have the product PD. So column by column, the left hand side is equal to the right hand side. And what does this imply? The ith column on the left hand side, would simply be API. That's the ith column on the left hand side. How about the ith column on the right hand side? On the right hand side, we have P1 to Pn and a diagonal matrix. So if we want to look at the ith column, what is the ith column on the right hand side? This is a product, right? So each column on the right hand side of the product matrix would be a linear combination of these column vectors P1 to Pn. But now, these linear combination coefficients are very special. For example, the linear combination coefficients for the first column will be D1 and then 0, 0, 0, 0. So all the other linear combination coefficients are 0 except for the first one. So the first column on the right hand side would be P1, D1. And similarly, the second column on the right hand side will be P2 and then D2. So if we equate the left hand side with the right hand side, this is what we get. On the left hand side, the ith column is API. And on the right hand side, the ith column is Pi scaled by Di. I goes from 1 to n. What does this equation mean? Does it have something to do with eigenvalue and eigenvectors that we have been talking all along? We have eigenvalues and eigenvectors here, don't we? API equal to dpi. So pi is an eigenvector of A with eigenvalue di. So when we have a diagonalizable matrix A, these P vectors are eigenvectors of A, where those elements, the diagonal elements of D, are eigenvalues of A. A question. We have this P matrix, the column vectors P1 to Pn. Would these P1 to Pn vectors form a basis for Rn? And that's indeed the case. Why? Because P is invertible. So P1 to Pn will form a basis for Rn. In this case, when A is diagonalizable, can we say A has n eigenvalues? Yes, indeed. Why? Because these are the eigenvalues. These D1 to Dn are eigenvalues of A. But of course, when we say n eigenvalues, we are counting multiplicity. So if an eigenvalue have a multiplicity equal to 2, then we count it twice. So some of the eigenvalues may be identical. Summarizing what we have discussed so far, we have theorem 5.2. A is n by n, A is diagonalizable. If and only if there is a basis for Rn that consists of eigenvectors of A. An example. B is this matrix, and the eigenvalue of B can be found out to be 3n minus 1. For each eigenspace, we can find a basis. For example, for the eigenvalue 3, we find an eigenspace WA3, and the basis for WA3 is this one. And we can also find a basis for WA minus 1. This is L2. The question is this B matrix diagonalizable? Well, we know a matrix is diagonalizable if there is a basis that consists of its eigenvectors. So now we ask if the eigenvectors will form a basis for R3. And now we have a basis for this eigenspace, and we have a basis for this eigenspace. So if the union of the two bases form a basis for R3, then B is diagonalizable. Let's call these vector P1, P2, and P3. And B will be diagonalizable. The answer is yes, B is diagonalizable if this P matrix is invertible. And we already have P1, P2, and P3, so we can easily check whether P is invertible or not. So we apply Gaussian elimination on P, and we find its reduced Roy echelon form, which is equal to the identity matrix, so we know P is invertible. So indeed, B is diagonalizable. And how can we express B? BP will be BP1, BP2, BP3. P1 is an eigenvector in this eigenspace, so it's a 3P1. And P2 is also an eigenvector in this subspace, so BP2 is a 3P2 as well. And P3 is an eigenvector in this eigenspace, so BP3 is equal to minus P3. And we can rewrite it as P1, P2, P3, and the diagonal matrix 3, 3 minus 1. Let's call this diagonal matrix D. Then we get BP equal to PD. We get BP equal to PD. Then B is equal to PD, P inverse. P matrix and D matrix can be obtained like so. A question. We express B as PD, P inverse. Are these matrices P and D unique? I will leave this question to you. Just now, when we try to determine whether this B matrix is diagonalizable, we first find a basis for this eigenspace, lambda equal to 3, and a basis for this eigenspace, and we look at the vectors in these bases, and we say yes, B is diagonalizable if these vectors are linearly independent, and that will make P an invertible matrix. It turns out that when we combine bases L1 and L2 together, the resulting set is always linearly independent, as we will see in the next theorem. Let L1, L2 to Lk be linearly independent subsets of different eigenspaces of A. Then the union of these sets is linearly independent. Let's draw a picture to see what this means. L1 and L2 to Lk, these are linearly independent subset of different eigenspaces. So we have Rn here, and we have different eigenspaces, W lambda 1, W lambda 2, W lambda 3. And in each eigenspace, we have a linearly independent subset. This is L1, this is L2, and this is L3. The theorem says if we take the union of these L1, L2, and L3, the union is linearly independent. This theorem is a more general form of theorem 5.3 in our textbook. This more general form is taken from another book called Linear Algebra by the same three authors as our textbook, Freeback, Insel, and Spence. If we apply this theorem on the previous example that we just work on, then we can immediately see that B is diagonalizable. This L1 is a basis for this eigenspace, so it's linearly independent, and this L2 is a basis for another eigenspace, so the union of L1 and L2 will always be linearly independent by the theorem. We will prove the theorem by induction. If we take the union of the first J sets, and we call the union L. If L is linearly independent, then the union of L and Lj plus 1 is also linearly independent. If we can show this, then by induction we have shown the theorem. Suppose this L, the set L that's the union of the first J sets, has vectors u1 to up, and Lj plus 1 has vectors v1 to vq. And what we want to show is that suppose this L is linearly independent, then these u vector and v vectors together are linearly independent. So what we need to show is that if we form the linear combination of these u vector and the v vectors, this linear combination equal to 0 would imply that all the linear combination coefficients are equal to 0. If we can show this, then this means these u vectors and v vectors are linearly independent. So that's what we need to show. But what do we know about these u vectors and v vectors? What we know is that AUI is equal to DUI for some DI scalar. I goes from 1 to P because each of these UI is a eigenvector of A. And we also know these V vectors are eigenvector of A, and they are eigenvectors of A in the same eigenspace. So AVJ is equal to lambda VJ for some lambda. This lambda is the same for all V1 to VQ. So these are the facts that we know about U vectors and V vectors. So let's try to use these property to show that they are linearly independent. These Vj are eigenvector of A with eigenvalue lambda. So this is the same as saying that Vj is in the null space of A minus a lambda identity. So let's try to multiply this star equation. We call this equation star equation by this matrix A minus a lambda identity. We make two groups. The first group consisting of these U vectors, and the second group consists of these V vectors. And we multiply this matrix to the first group and to the second group. So now we have two terms, the first term and the second term. What would be the second term? What would be the second term? Remember, each Vj is in the null space of this matrix. So we get 0 for the second term. Now let's look at the first term. Here, for the first term, if we multiply, use distributive law, then we get p terms. And we look at each terms separately. For the first term, we get this matrix and then A1, U1. And what is this? The matrix vector product AU1, then we get D1U1. And for this term, lambda identity U1, we get lambda U1. And we can pull out U vector. So this is the first term here, the product of this matrix and A1, U1. And similarly, for the second A minus lambda identity matrix, we multiply with the A2, U2, then we get this term A2, D2 minus lambda U2, and then all the way to AP, DP minus lambda UP. Alright, so this is equal to 0. this is what we get so far. But we know that these u vectors are linearly independent by assumption. Remember, we assume that this is linearly independent. If this is linearly independent, we want to show the union is also linearly independent. Alright? So these u vectors are linearly independent and the linear combination is equal to 0. That means that all the linear combination coefficients are equal to 0. So this implies ai di minus lambda is equal to 0. I goes from 1 to p. We have one scalar and two scalar. The product is equal to 0. So one of them must be equal to 0. Can this di minus lambda equal to 0? Can it? No, this is not possible. Why? Because di is eigenvalue and lambda is eigenvalue of another eigenspace. So di and lambda are different. So this cannot be equal to 0. If this is not equal to 0, then that means only one thing. ai is equal to 0. So ai's are equal to 0. I goes from 1 to p. Now in the star equation, all the ai's are equal to 0. We are left with the second part, the linear combination of these v vectors equal to 0. But then v vectors are from this set, Lj plus 1. Lj plus 1 is a linearly independent set. So this implies b coefficients are equal to 0, a coefficients are equal to 0, b coefficients are equal to 0. So there we go. All these u vectors and v vectors are linearly independent. Some questions. Suppose we have a n by n matrix A. S is a set of q vectors, and each of these vectors is an eigenvector of A, and these pi are eigenvectors corresponding to distinct eigenvalues of A. So each pi corresponds to a different eigenvalue of A, and all these eigenvalues are different. Is S a linearly independent set? Would S be linearly independent? Well, if we look at what this says, it means that each pi comes from a different eigenspace. They all come from different eigenspace. So when we put together by the theorem that we just talked about, the union would be a linearly independent set. Yes, indeed, because each pi has a correspond to a eigenvalue, and all these eigenvalues are different. So S is linearly independent. Now suppose A has n distinct eigenvalues. So A has n eigenvalues, and all these eigenvalues are different. D1 to Dn, they are all different eigenvalues. Is A diagonalizable? For each di, we can find corresponding eigenvector pi, right? By definition of eigenvalue, if we're given eigenvalue, we can find a non-zero solution to a particular to find non-zero solution to a homogeneous equation corresponding to that eigenvalue, then we can find eigenvector. And all these pi vectors, when we put it in a set, is linearly independent because they all come from different eigenspace. So indeed, these pi will form a basis for Rn, and A will be diagonalizable. A is diagonalizable. So here's an algorithm for matrix diagonalization. Suppose A is n by n, and we know that A is diagonalizable. So A is already known to be diagonalizable, so there is a basis for Rn that consists of eigenvectors of A. Then here's an algorithm that can find the diagonalization, find those P matrix and D matrix for us. So first of all, we can find all the eigenvalues of A, and then for each eigenvalue, we find the corresponding eigenspace, WA lambda. And then we collect the vectors from the basis of the eigenspaces to form P. Then we have the diagonalization of A. This algorithm works if we already know that A is diagonalizable. But how do we know whether a matrix is diagonalizable to begin with? To answer this question, let's look at one example that we had earlier. A is this matrix, and we know the characteristic polynomial of A is given by this polynomial. And we have found that for lambda equal to 4, the multiplicity is equal to 1, and the dimension of eigenspace is equal to 1. And for lambda equal to 2, the multiplicity is equal to 2, and the dimension of the eigenspace is equal to 1. For this example of A, is A diagonalizable? From what we have learned earlier, we know A is diagonalizable if we can find a basis for Rn that consists of eigenvectors of A. For this A, we have two eigenspaces. One is W4, WA4, and the other one is WA2, and the dimension of this eigenspace is equal to 1, so we can only find a linearly independent eigenvectors here. And for this eigenspace, for the eigenspace WA2, the dimension is also equal to 1, so we can only find one linearly independent vector in this eigenspace, but we cannot find more than one. And similarly, for this eigenspace, we can not find more than one linearly independent eigenvectors. So would A be diagonalizable? Sorry, this is R3. This is R3. So in this case, we can only find two linearly independent eigenvectors. One from this eigenspace and one from this eigenspace. But to have a basis, we need three linearly independent eigenvectors. So we are one vector short. And there does not exist a basis for R3 that consists of eigenvectors of A. And an alternative way of stating theorem 5.2 is that A is diagonalizable if and only if the sum of the dimension of eigenspaces of the different eigenspaces of A is equal to n. The sum of dimension of eigenspaces of A is equal to n. Equal to n exactly. We know this sum can be smaller than n, as we have just seen in that example. The sum can be smaller than n, but can it be larger than n? Can the sum be larger than n? What do we know about the dimension of an eigenspace? We know it's always less or equal to the multiplicity of this eigenvalue. And we know the eigenvalues are roots of the characteristic polynomial, which has degree equal to n if A is n by n. So the sum of the multiplicities will be the total number of real eigenvalues, and this number should always less or equal to n. So, going back to the question, can this sum be larger than n? No, it cannot be larger than n. So now we have the sum of the dimension of eigenspaces is less or equal to the sum of the multiplicities of all the eigenvalues, and this sum is less or equal to n. And we know A is diagonalizable if this sum of dimension of eigenspaces is equal to n. And we have two inequalities here, an inequality here, and another inequality here. For this term, for this summation to be equal to n, then we need both of these inequalities to become equalities. This is inequality should become equality. Equality. The first inequality here becomes an equality if the dimension of each eigenspace is the same as the multiplicity. If A has n eigenvalues, counting the multiplicity of all the eigenvalues, then A has n eigenvalues, real eigenvalues. Summarizing, we have this test for diagonalizable matrix. A n by n is diagonalizable if the following two things are true. First of all, the total number of eigenvalues, each counted as often as its multiplicity is n, and the dimension of each eigenspace is the same as the multiplicity of that eigenvalue for each eigenvalue lambda of A.